Okay, continuing with section 1.3 for MAC 1105 application problems. We were almost through with the second problem. We had just found out that the salary for the bachelor's degree turned out to be $81,000, and in the process of finding the master's degree salary, which is based on the answer that we just found, the X value. So the master's degree is twice that amount and then 70,000 less. So 2 times 81,000 minus 70,000, you can put that in your calculator. So that would be 2 times 81,000. Take away 70,000 from that, and you get 92,000. And that would be the master's salary. So we now have our two salaries. This is the master's, this is the bachelor's, and then you want to be able to check those answers. So in the wording of the problem, they had said that the two salaries combined was $173,000, and I extracted that wording for you. So let's just make sure that our answers check out. 81,000 plus 92,000. And let's see if this is actually true that they combine to this amount. So go ahead and again, check your answers. This is one of the salaries. This was the other salary according to the way we set up the expressions. And yes, that does check out to add up to 173,000. Okay, so the next problem, or the next two problems, concern consistent trends of either growth or decline, but the same amount is occurring every single year. And when we have a consistent trend in either growth or decline, the graph of that situation is represented by a line. So these are called linear models, and you know that they are happening whenever there is a suggestion that there is consistent growth or consistent decline. So the first scenario is one concerning growth. In 2014, the average age of cars on the U.S. roads was 11.3 years. That means that when they started this observation where they were observing the average age of cars, the very first, when no time had passed at all in the observation period, 0 years had transpired, the average age of a car was 11.3. For the period shown, this average age increased by approximately 0.2 years per year. So every year that they continued to observe the average age of cars, the average age was jumping in consistent increments of 0.2 years per year. If this trend continues, how many years after the year 2014, that's the year in which the observation period began, how many years after 2014 will the average age of vehicles on the U.S. roads be 12.3 years old? So the catch to this problem is knowing how to represent the linear equation, which again is suggested by the fact that there is a trend in growth. The trend means that consistently every year it is growing by the same amount, if the problem happens to be about growth, which this problem does. So you're not talking, 1 year the average age grew by 2 years, and then the next year the average age has grown by 5.5 years, like different amounts each year. It's a consistent amount, even though they couldn't be that high because it's just happening per year. But the point is that the growth, the amount of growth that is being experienced in the average age of a car is the same every single year. That's what makes this a linear equation. Therefore, we have the right to use equations and formulas that have to do with devising linear equations. So we have those formulas that we can use. We just have to understand what each bit of information stands for. So let's answer these questions to kind of lead you through this problem scenario towards an equation that we're going to develop. What was the average age of cars when the observation began? And that would be this. When the observation began, no time had transpired. It was just the original average age before they continued to watch these ages grow. So what was it when it began? 11.3 years. And you can put the title there or just the 11.3. What number represents the consistent growth? The consistent growth trend is represented by the 0.2. Every year, the average age of cars is growing by that much. Plot the average age at the beginning. Again, average age at the beginning when no number of years had transpired with respect to how long they had been watching the average age of cars. So 0 years have transpired. That means that's the same thing as saying at the beginning of the observation period, the average age of a car was 11.3 years. So, and we even have that information right here. You can label the x-axis with the word years that have transpired in the observation period, 0, 1, 2, 3, etc. And you can label the y-axis with the average age of the car, or just age of a car, just, so you're not writing too many words. Okay, so after they've been watching the average age of cars for 1 year, it jumps in increments of 0.2. Remember, there is a consistent jump in the average age of a car of 0.2 each year. So if I was to add 0.2 right here to this y coordinate, I would be up to 11.5. And if I was to add another 0.2 to the 11.5 that I just had, I would have 11.7. So it's consistently jumping up in increments of 0.2. That jump is never changing, which is what makes it a linear equation. This is the average age of a car at 0 years, meaning the beginning of the observation period. This is the average age at 1 year, average age at 2 years, and you could go on with that, but I've only asked you for 3 points. So let's go on to actually plot them and write the equation on the next page. So on the next page, it says, notice that the points have a linear trend. You will notice that once you go to plot them, which is due to the consistent rate of increase. And that consistent rate of increase, again, is the 0.2 that they talked about. What formula allows you to write a linear equation that models this line? Well, the 11.3 that you got, the average age at the beginning, is what we call the y-intercept. The reason that we know it's the y-intercept is because let's think about the x partner that was with this number. Any point, any y value that has an x partner of 0 is known as the y-intercept. And in fact, when you go to plot it, it will be a point on the y-axis. That's what a y-intercept is. Described verbally, it's a point on the y-axis. Numerically, it is a point that such that the y partner has an x the y coordinate has an x partner of 0. That is how you could describe it numerically. So I know that that's the y-intercept. And then whenever you have a consistent growth rate, that consistent growth rate is known as the slope. So this would be known as the slope, or what we call the m value when you're writing linear equations. And this is called the y-intercept. And in the linear equations formula, the y-intercept is actually called b. So if you don't remember this formula, the formula that allows you to write a linear equation, this is one way of writing the linear equation, is called the slope-intercept formula. Just kind of abbreviate that there. And we have both of these things. We actually have the slope, which is that 0.2. It's growing in that consistent increment each time, times x, plus the original average age of a car. So we have a linear equation, and it says use the equation you've written to solve the problem. Consider your labels for the x-axis, which we spoke about on the previous page. The x-axis is going to stand for the number of years that they've been observing car ages. So we would just call this 1, 2, this would be the 0 mark right here, 3, etc. And then the average age of a car started at 11.3. So we could call this 2, 4, 6, 8, 10, 12. I mean, all of these points are going to be extremely close together only because they're only jumping in tiny, tiny increments, which is increments of 0.2. So when we go and plot the points that we had on the previous page, remember the first one was 0 and 11.3. So that's going to be about, let's see, this is 10 right here. So 11.3, let's just say it's right there. That was the first point. Then the next point, which again is on the previous page, it jumped. The years jumped from 0 to 1, and the y-coordinate jumped from 11.3 to 11.5 because we kept adding 0.2 to this. And then the third point was at 2 years, it was 11.7. So again, the reason that these line up in a straight line and that line is slanted is because of the consistent growth in the y-coordinate. So we'll just say that at 1, it's just a smidgen higher, and at 2 years, it's slightly higher than that. So it's very slowly increasing upward and to the right. And the fact that this line is climbing upward, that signifies growth. And this is the number of years that they've been observing car ages, while the y-coordinate is the average age of the cars at 1 year, at 2 years, at 3 years, even at 0 years, which was the y-intercept. So when you go to answer this question, when 12.3 years is plugged in for the appropriate variable, you can then solve for the x value that's associated with an average car age of 12.3. So they're telling you that this 12.3 is an average car age, and the y-axis, the y value in this equation, is where you would plug it in. So if we were to work with that, we would have our equation. Y is equal to mx plus b, which we had plugged in the 0.2 for, and our initial average age. We are now using that to answer a question. When the average age, which is what y stands for, again, look at how that y-axis is labeled. It stands for the average age of cars. Therefore, any number with that title gets plugged in for y. And then you can just solve for the x value that's associated. If they were to ask you, okay, when is the average age, how many years would it take for the average age of a car to be 18.7? Then you would put the 18.7 in here and then solve for x to find out how many years it would take for cars to reach an average age of 18.7. You can put any number in here you want. And then by knowing how to solve an equation using inverse operations, you are able to solve for x, which we will do in the very next video.